Welcome to our overview of our DSC 180 Capstone project. My name is Hiroki, and I work with Jared and Cyril while we spent the past 2 quarters working with the Intel telemetry team to develop solutions for aging computers. Computers have gotten faster and faster as technology advances. This also means that attention spans for users have gotten shorter. A 2003 study on user attention of website load times showed that 0.1 seconds is the limit for feeling instantaneous response. 1 second is the limit for keeping the user engaged to the current task. And 10 seconds is the limit for keeping the user's attention on the current task. The rapid progress in technology also means that hardware can quickly be left behind. Many offices have decade-long upgrade cycles, with some still using operating systems like Windows XP. Modern apps built with modern specs in mind cannot start up on older computers in reasonable times. Some everyday applications can take over 30 seconds to load on some machines, far longer than the 10-second limit of attention. The solution is simple: preloading applications. By preloading, the application can open near instantaneously when the user clicks the icon to start the program. So, even with an aging PC, this technique can give a snappy impression to the user. However, this solution has its own problems. Firstly, PCs often have many applications. We cannot preload all of them, especially on older PCs, due to multiple reasons. First, preloading too many applications at once will also cause a severe performance issue due to lack of CPU power. Second, we cannot preload and keep many applications running in the background at once due to RAM limitations. So, for our DSC 180 project, we aim to tackle the issues presented previously by predicting future user behavior and preload only select applications. First, we collected user data with programs built with Intel's System Usage Reporting, SDK. Then, we built machine learning models trained on the user data collected. Finally, we use these models to predict future user behavior and predict applications the user may open next.
Now, we'll explore the first half of our project, where we focused on creating the programs to collect the user data that we'll use to predict app loading later on. We use C to develop programs with the Intel SDK, known as input libraries. These input libraries track user and PC activity and log them in databases. So, why did we use C here? Well, C provides us fast execution times compared to more higher-level languages such as Python. We also have tight integration with Windows APIs. We have numerous convenient macros that allow us to access data, and data structures that are well-suited to the type of data we're collecting. Our input libraries collected the data shown in the image, which we will now detail in the following slides. So for a brief high-level overview of our input libraries, our first input library, the mouse input, collects the X and Y coordinates of the mouse at a fixed interval. Our second input library, user weighting, logs the current mouse icon at each user click. Some examples of mouse icons are the standard pointer arrow that you can see below, as well as the hand or the I-beam when you hover over text. Our third and fourth input libraries collected foreground application, or the application with the foremost window, and the applications behind it in descending Z order. Now let's move on to quarter 2, where we actually use the data collected in the previous quarter to create our models. Once we built our input libraries, we ran them on 2 computers over the course of 3 months. Each input library continuously collected usage data of each machine from PC startup to shutdown. Once all this collection was done, we collected over 160,000 rows of data. For some exploratory data analysis, we were aided in this process as we had to do minimal data cleanup. This was because we were deeply involved in the collection of the data, so we built in checks and validation processes so we didn't have to do as much work in this stage. We found that each computer had separate periods of high and low usage. For example, when the desktop was being used much, the laptop wasn't used as much, and so these kind of have an inverse relationship. We found that these periods of usage were split into fall quarter 2021, winter break, and winter quarter 2022. So these were aligned in the context with which both of these devices were used. If we take a look at our top foreground applications, we can see that the Chrome and Explorer are the most used for both devices. However, there are some changes after that.
So once we cleaned and explored data, we focused on our 2 main predictive tasks. Our first task was to predict future foreground applications, and we did so by using 2 different models, a hidden Markov model, and a LSTM model. Our second task was to predict the time usage in minutes of future applications. Again, we use an LSTM for this task. As mentioned, our first model for next app prediction was a hidden Markov model. So what exactly is a hidden Markov model? An HMM is a type of model that views events as a continuous sequence. For example, an input sequence may be the events of Chrome, Discord, then the command prompts. The hidden Markov model then takes these sequences and computes conditional probabilities of each unique pair of foregrounds. For example, the probability of Discord following Chrome may be 25%. Now, why do we choose to use a hidden Markov model? A hidden Markov model is a perfect model to solve a time-related problem, such as our next app prediction task, where each sequence has a notion of before and after. In our case, we have past foregrounds that lead to predicting future foregrounds. How do we do this? By manually implementing a first-order hidden Markov model. We base the structure of our HMM class on the fit predict structure found in the sklearn, another machine learning library. Once trained on a single user's data, our model outputs a matrix which shows the probabilities of each application appearing directly after another specific application. For example, when currently on the DB browser SQLite application, Chrome.exe has a 14.7% chance of becoming the next foreground application. This can be easily visualized with the bar chart on the right. For our predict function, we have an optional parameter of n foregrounds, which indicates the number of foregrounds the model predicts for each input listed in the order of highest probability. With an n foregrounds of 3, the model predicts the 3 most likely applications to appear after a single input application. Thus, in order to determine whether or not a single instance was accurate, we checked if the true foreground, future foreground of the input existed within the list of predicted applications. With an n foreground of 3, we achieved an accuracy of approximately 70% for our laptop data, and we have similar model performance with our desktop data as well. However, one concern is that the model will heavily bias towards applications that are frequently used, such as Chrome and Explorer.
Our second model we developed was the LSTM RNN model. In order to create our model, we used a Python library called Keras. Keras is a deep learning API that allows us to create and test various machine learning models quickly. By using the built-in functions, we can streamline our model creation process. Using Keras, we wanted to create a recurrent neural network, or RNN. A RNN is a type of neural network that uses previous inputs to make new predictions. So, in our case, it would use the recent past history of computer usage by the user to predict the user's next move. This image here is a visual representation of a RNN. The question we want to solve is, given the current situation, what app is most likely to be launched next? So in this situation, we thought it'd be best to use a long short-term memory model, also known as a LSTM. A LSTM is a type of RNN that is more tailored for situations where the durations between events vary. In our case, duration of time between each application is different, so a LSTM is a good fit for a use case. This image here shows the inner workings of a LSTM model. In order to create the model, we needed to select the data to use as features out of our data set. We decided to use 3 different parameters. The first is the time the foreground changed. The second is the application opened right before the one we were attempting to predict. And the third is the time the user spent on the application at that time, shown here as time delta. In order to make our data compatible with the Keras model, we needed to make a few pre-processing changes to our data. First, we obtained the top 10 most used applications in the dataset and renamed the rest to other. We found that some applications only showed up once or twice in the dataset, and omitting these during training raised our model accuracy tremendously. Then we extracted the hour from the timestamp. Then we created the output column by shifting the application name column by 1. Finally, we would not encoded the application names to create our final feature set. After pre-processing, we split the data into training and test sets with a 70-30 ratio.
Here you can see a high-level overview of our model. Our LSTM consists of one LSTM layer, one dropout layer, another LSTM layer, and finally a dense layer. The code here shows the different layers of our model and the intuitive way Keras allows for model development. On the right, you can see a diagram of our model as well. Now, let's explore the different components of our model in detail.
Our code has two LSTM layers. The LSTM layers utilize backpropagation through time and the structure of memory blocks connected through layers. As we mentioned before, this is sort of similar to how the human brain thinks, and thus why it's well suited towards tasks emulating human behavior, as we're using it now. These predictions that the model makes are thus informed by previous events.
Next, our dropout layer reduces overfitting. It does this by randomly setting input units to 0. In this case, we set 0.2 or 20% of our data to 0. Finally, our dense layer is, as the name implies, a dense neural network layer that accounts for the categorical variables within our data. In this case, our categorical variables are our unique foreground applications.
You can see our model accuracy was 68.6%. Similarly to our Hidden Markov model, we obtained the top 3 predictions that were made by the model, and then calculated the accuracy by counting the time the actual app appeared in the list of 3 predictions.
For our second task, we wanted to predict future foreground application usage time. Again, we use an LSTM model for this task. Unlike our previous LSTM, which uses only a single previous instance to predict the next instance, we use the previous 5 instances to predict the next in this LSTM. This would result in greater predictive power for our regression-based problem of predicting foreground usage in minutes. Each training input is a 5x1 vector, which includes the 5 previous foreground time usages in minutes. Each block of 5 previous durations are input to our model sequentially, passed through various network layers, and then finally arriving at an output prediction. As previously mentioned, our model will use the previous 5 time durations to predict the single next duration. Therefore, we have a shape of this. Each input will have 5 features, each feature being a time step, and will output a single next duration in minutes. Once trained, we have a mean absolute error of 0.74 minutes. However, to fully understand what this mean absolute error signifies, we calculated the mean foreground duration, which was 1.73 minutes. Therefore, on average, our model will have an error rate of 42.77% off from the true time duration. We believe that these results are promising because this error rate would indicate that for the majority of the time, we have prediction window as shown here. The prediction will be just shy under a minute incorrect, still capturing most of the user's application duration.
Here are closing thoughts on the past 2 quarters. Throughout the project, we faced multiple challenges that we had to overcome. In the first quarter, we were tasked with creating input libraries in C. However, all 3 of us had minimal C programming experience coming into the quarter, so we had to learn very quickly as we built our input libraries. Despite this, we created 4 complete input libraries that collected data successfully to set us up for the second quarter. We believe that if given more time or more past experience, we could have built even more fully fledged input libraries that could have extracted secondary features to improve our model performance. Overall, though, we were satisfied with our performance in quarter 1.
In regards to our data collection, our collected data span several distinct time periods, such as fall quarter 2021, winter break, and winter quarter 2022. One concern was that we did not establish clear boundaries between these periods, allowing the potential for patterns within our data to overlap and reducing model performance. Also, we could have collected more data by running our collectors on more machines in an attempt to generate insights within those users' data sets. Also in quarter 2, our Hidden Markov model used to predict the next future foreground was based on a first order model, which only had a look back of 1 event, hence the name first order. We could have added more predictive power by incorporating second, third, or even higher order Markov models. However, we instead decided to devote more of our time on developing our LSTMs.
Now, we've gone over our work in the past 20 weeks in detail. So what? Well, we saw that being involved in the collection process as data scientists provided us valuable insights that we wouldn't get otherwise. Usually, we're just provided with the data. But in the past weeks, we've actually developed the collectors that gave us the data, and we were able to do things in certain ways that allowed us to not have to clean the data as much later on. And we were able to verify our data and sanity check it in the collection process itself, which gave us an unprecedented level of control over the quality of the data. In terms of practical implementations for our work, an obvious one that stands out is on the mobile side. We can use frameworks such as OpenVINO to deploy our models on mobile devices.
To run on-device machine learning to predict mobile apps that way.
In addition, we can target our models towards older devices that don't have the processing power to run apps as fast anymore. Lastly, we could transfer our models to the cloud, distributing our training over cloud servers versus having it trained on the device.
Thanks for taking your time to watch this presentation. If you have any questions, please feel free to let us know.